Hi, my name is Jamie Hood, and I'm presenting my experimental demonstration on how a ferrite choke works to cancel out noise in electronic devices. You have probably seen several of these devices in your desk drawer or behind your TV console. The ferrite choke is added to electronic cords to reduce the amount of noise or electromagnetic interference reaching the input. First, I will explain how a ferrite bead relates to the course material. We have learned about Ampere's law and that a current-carrying conductor will produce a magnetic field in the tangential direction per the right-hand rule. The magnetic flux in the ferrite bead is proportional to the magnetic field, however, not directly proportional as it is in a linear medium. Faraday's law states that a time-varying magnetic flux will induce a voltage and thus a current in a stationary conductor, with a magnitude that's proportional to the time rate of change of the magnetic flux and in the opposite direction per the right-hand rule. In other words, the current is induced to maintain the previous flux in the ferrite bead. Through these equations, we know that the induced voltage is proportional to the time rate of change of the current. As can be seen in the illustration, the low-frequency signal has a much smaller slope than the high-frequency noise. Therefore, the voltage induced from the changing magnetic flux of the low-frequency signal is much smaller than the voltage induced from the changing magnetic flux of the noise, which cancels out only the noise and allows the signal to pass. I'm going to go through the test setup for our experiment. Here we have a function generator or a signal generator, kind of an old school one, but it goes down to the hertz range, below kilohertz, and it goes all the way up to 20 megahertz. This is going to give us a signal, and I'm going to sweep across all those frequencies. From the output, so it's going to output the signal here, it's going to go through our transition here. We have signal and ground, and it's going to go up into the spectrum analyzer. And this is going to show we're seeing power in dBm versus frequency from kind of DC all the way up to 20 megahertz. So first I'm going to do a baseline test, and this is going to be without any ferrite choke. So what I'm going to do is I'm doing max hold, so this is going to save the maximum value of amplitude. I'm going to sweep all the way through, and it's going to hold the maximum value. And if we kind of go slowly, it'll overwrite any oscillations that it picks up. So I'm going to try to move through here sort of quickly for the purposes of the demonstration, and I'll be able to clean up the data later for plots, etc. So here we see this baseline data. So after I get the data, I'm going to add the ferrite choke, and we should see attenuation of the signal, or we should see the amplitude decrease in the higher frequencies, which is what these are supposed to do. They're supposed to cancel out noise. So I'm going to put this on the signal. We sweep backwards this time. We'll see that the amplitude is decreased by 3 dB is kind of what we're looking for. That'll give us half power. And now if we are to switch this out for the larger ferrite choke, we'll see that amplitude diminished even further. So I'm going to sweep the frequency again, and we'll see the amplitude is diminished even further. So the ferrite chokes can be a very effective way of canceling out high-frequency noise. They act as a low-pass filter. It's a very simple passive device, and it's a great example of electromagnetic principles in our everyday lives.